on the three criteria. First one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express different from the three criteria? The second one, expressiveness. How can we express and then we use a target compiler to 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 and then we use a target um, and and by and then you need to deploy a monolithic P4 code or programmable code, whatever P4 or other programming language on top of it, and the hybrid programmable in which you may have actually a fully working pipeline, maybe doing all the standard stuff like routing and bridging, and on top of that you can on your add your own logic. Sorry. In addition to that, that device may be runtime programmable, and you can load the multiple program on the same time, because and this is the idea behind that. From that, I will move to if my computer will allow me. Okay, describing actually NVIDIA Spectrum switch architecture. It's important to me to introduce that to you because it's quite different than Fina. You will see, and we will talk about that. Some of the assumption that were assuming the previous talk does not exist in our talk. This is a full DRMT implementation, meaning that there is a disaggregation between lookups and lookup logic. Memory is fully shared. There is no fixed pipeline stage, so you can do as many lookups as you like. It's a go-to completion model. We have multiple go-to completion CPU. We can guarantee line rate, and we have a very sophisticated scheduler. So pipeline can be in a different sizes, no limitation of the number of lookups. You can go back to the same table more than once. All the known limitation from the PISA architecture and the RMT does not exist on our targets. There is fully decoupled between the logic and the lookups. All the memories dynamically allocated, table memory like logic memory and data itself. In addition to that, it's fully dynamically programmed, meaning that you can load pipeline in runtime. Pipeline can be portion like a new VNF, the new function. You can edit existing one. You can even edit the parser and all that in runtime with zero downtime. And actually, there is a paper for around that area in the coming NSDI, a paper we published together with Rice University. And in addition to that, in Spectrum 4, we added the stateful engine. The stateful engine can actually hold states, and which make implementation function like a stateful firewall or SLB much easier to implement. The way we envision that programmability is a way for the user to just deploy a new container with a new logic on top of an existing fully functional switch within the fabric. So it's not like write it everything goes zero. Like writing a switch NOS from the scratch, it will take years of development. We would like deployment of a new network function to become in a matter of weeks, months, and so. So the idea behind that is write only what you need, customize your function, and load only it to a working system. So by doing that, you can really deploy things that look like a firewall or load balancer or others in a working network without the need to deal with the legacy. And when I'm saying deal with the legacy, I'm referring both to the hardware pipeline and to the software stack. So what we created is a framework of extension for both, for the pipeline and for the software stack as well, on top of Sonic. I will skip that one because I believe it's too details. And in the sake of the time, this is more or less our compiler infrastructure. Something that I would like to say here, it's the same architecture for the DPU and the switch. So all the things that I'm just mentioning will be applied to the DPU as well. And you will be able to program them in the same way. So you can take a P4 program and choose where you want to load it, whether you want to load it on the Bluefield DPU or you want to load it on the switch. Sorry. Of course, the Bluefield DPU will have more functionality in terms of programming model. it will be more flexible and the switch will be more powerful in terms of speeds and feeds. I didn't mention that, but Spectrum 4, the stateful device is going to be 50 terabit device. So this is the workload, programming workload in which you can compile your P4 program on a remote compiler, off-box compiler. We deliver, we provide the container, a fully functional Docker container with all the essential and all the dependency. So it's quite easy to write a P4 code there. There are examples like a low word example, P4 low word example provided with our compiler, and then this the outcome of the compiler, the binary blob that is created in the compiler. We are loading that into the DPU on switch. We support P4 runtime API, and I didn't mention that, but I assume that it's stated obvious that we support P460. Two use cases that I would like to touch in a very fast manner. One of them is SDN appliance or cloud bare metal provisioning. There is a huge, like a use case that we see in all the cloud provider basically. And the problems that they are trying to solve is actually connecting the bare metal devices into the cloud, into the cloud infrastructure. Usually nowadays, the state of the art is to have an FPGA between the bare metal and the virtual machine. The FPGA is too expensive. The programming model is not so trivial, and it's not standard. So there is a trend to move from FPGA based to an P4 based devices. DPU or switch doesn't really matter. Some are doing that and some are doing that. The idea behind that is to take all the cloud pipeline, which you see underneath in the bottom part, a very abstracted version of it, like some kind of a policy, then connection tracking, then routing, tunnel, and then underlay routing, like overlay routing, and then underlay routing. One good example for that can be observed in the Dash repo. Dash is an open source project led by Microsoft Azure to do exactly that. Another use case that I would like to mention is actually a project we are doing under the MARSAL umbrella, and it is AI-based firewall. The idea behind that is we would like to have a classification based on AI, CNN, to be more exact, and the idea behind that is to take the byte stream of a packet, translate it into a very low resolution picture, describing the patterns of it. And the nice part is that this initiative can actually detect application even if the data is encrypted. So we are not building on the data itself, the UDP source port or other data. It's actually taking only the pattern, like the packet size, the jitter between them, and a few other parameters, and according to that, detect the application. This is the pipeline in high level. We get an encrypted data, do some processing, send some feedback to some classifier, which runs CNN, and then the classifier using P4 runtime can actually configure firewall rules. This is my last slide. Thank you for listening.
Okay. Okay, thank you. So I'm very happy that I'm the last presenter, because actually what I'm going to talk about is not an actual finished work or some nice new use cases that we found for P4, but much rather pretty much work in progress process where we are trying to think how and in which way to evolve software-defined networks and programmable data planes into the future. So it's basically just a couple of these discussions, mostly between researchers working on programmable data planes in general, and mostly with Gianni Antichi from Queen Mary. The paper is actually presented at the SOSR 2020, so I would just really like to maybe summarize the most important findings that we've made. Like after tens of years of, basically 10 years of working on SDN and programmable data planes in general, we made a couple of observations, and in this talk I would just like to make the case for three observations that all seem to act towards the same goal. We need to extend software-defined networking, and of course the protocols and the mechanisms and frameworks that we come to expect for SDN to work, including P4, towards the application layers. So the idea here is that the traditional fixed function Ethernet bridges handle packets at layer 2, IP routers, of course, at layer 3, and then we kind of see some sort of limited transport layer traffic processing at middle boxes. And the nice thing about the software-defined networking was that it's actually just opened up all these network policies that usually were hard-coded into a fixed function device, so that we can now program them from a central controller. Our observation and our proposition is to actually just it's time to extend software-defined networking from this limited set of layer 2, layer 3, and partial layer 4 forwarding architecture towards the full stack architecture, that we can also just process application layer protocols in like, for instance, P4. So basically that's all the talk. But of course, I want to just elaborate on these three observations that seem to be all pushed towards the same goal. But I will leave you with that. At the end of the talk, I will not give you answers. I just like to give you the challenges and the questions. Okay, so we started from Cloud 1.0, when monolithic applications were deployed into full virtual machines. Of course, virtual machines contain all the operating systems and the network stack with that. So basically, in this case, VMs consume traffic at layer 2 and layer 3. So for the actual programmable data plane layer, which is mostly just everything underneath this layer, it was enough to actually understand what's going on at layer 2 and layer 3, and you didn't have to process packets all the way up into the network stack, because it was enough for virtual machines that actually just the main communication pattern used to be layer 2 and layer 3. Now we are moving to microservices, which is, of course, all you know, is fine-grained decomposition of business logic, where we have loosely coupled microservices isolated in lightweight Linux containers. But the most important change that we are seeing right now is that microservices actually consume and expose services over application layer protocols, HTTP, gRPC, SOAP, WebSocket, everything that we now do over Kubernetes and most in service meshes is application layer protocols. So the first observation, the first takeaway, is that with the transition from Cloud 1.0 to Cloud 2.0, we are seeing the main network communication pattern to change from layer 2 and layer 3 to application layer protocols. The interesting things these days are happening at layer 3, at layer 7. What are those interesting things? Let's just try see a microservice as it is written today. This actual model is taken from a production service that we've developed with a large telco vendor. The case here is that microservice communication, in this case, depends on these layer 7 network functions that are hard-coded into the application. Of course, when your service actually consumes traffic at layer 2 and layer 3, that is left to the actual application to contain the entire network stack and process everything all the way up to layer 7, which means that layer 7 network policies are actually hard-coded into the application. Even though we would like to do interesting processing in a programmatic way at layer 7, like load balancing, application layer, access control, circuit breaking, hash checking, encryption, policing, everything, so you name it, these things cannot be programmed. We cannot impose layer 7 network policies centrally from a central control plane, because everything is hard-coded into the application. Okay, quick example, HTTP REST API calls, you want a microservice that can only be reached from another microservice via a read-only API. Of course, this actually means that when you do this on HTTP, you will have to filter on HTTP methods, let get requests through, but block HTTP post request. The problem is that for a traditional layer 2 and layer 3 SDN switch, like a P4 switch, all these things look the same. They are just HTTP protocols. The port is the same, protocol is the same. You cannot really take a look into the traffic and be able to selectively block or accept different HTTP requests, which is a major blocker because the network cannot filter connections based on the HTTP header fields. And then we cannot really impose layer 7 ACLs in switches. Another problem where we don't have enough visibility into network traffic is VXLAN. Traditional switches do not process packets all the way up to the VXLAN tunnel IDs, which is a bad thing because actually in production we were actually faced with this requirement, trying to understand the VXLAN network identifiers and be able to route traffic based on that. A final example is again comes from production. We would need to be able to police traffic based on real-time protocol streams. If you know, real-time protocol is actually used to encode audio and video samples communicated over the internet in a real-time manner. Problem is that the traffic is not processed all the way up into the application layer real-time protocol header fields, and this is a major problem because we cannot selectively block and accept or police individual RTP streams. Even bigger problem is that we don't really have enough application layer metadata inside the virtual network to be able to just make sense of an RTP header and trying to match, for instance, an RTP SSRC to an actual call ID. So the second takeaway is that application network protocols should be moved out from the applications. We no longer want to encode layer 7 policy in the application. We want to move all these things into the data plane and allow the enforcement of layer 7 network policies centrally. Okay, and the last observation that we are making is that, of course, the service mesh is the thingy that is doing this right now. So if you look at Istio, if we are using Kubernetes with any service mesh, you see that the service mesh is exactly a layer 7 SDN. So this seems to be the answer. A service mesh can actually process packets all the way up to the HTTP or other application layer header fields, understand proxy, route, load balance, reconnect, retry, circuit break, any layer 7 protocol connection. This is achieved by injecting a service proxy into the data path. Our observation here is that it is not just that this model is super inefficient. This is not our observation. This is basically now, I think, a common sense that when you actually just process traffic from an application to another application, you have to cross the virtual switch at least 3 times. And of course, you have to just process everything through the service proxy 2 times. So this is not really efficient. The even larger problem that we are seeing today is that layer 4 and layer 7 network policies are now programmed completely separately from layer 2 and layer 3 policies, and there is nothing in between to actually be able, that there is no way to actually being able to converge or synthesize all these different network policies into a full stack policy. The sidecar proxy model is not really efficient. We cannot really go on with this model, I think, anymore. This is cool for service meshes. It's cool for TCP and HTTP, because for HTTP, this sort of works. The problem is that as we are trying to move towards higher performance and traditional telco protocols, this model does not really work anymore. So the state-of-the-art layer 7 software-defined network service meshes, they are restricted to HTTP, do not really work for our well-known telco protocols, and it runs on top of the inefficient sidecar proxy model. Okay. Our proposition was to actually, and our ongoing work is extending the data plane, and of course, with this, the data plane programming frameworks like P4 up in the protocol layers. Okay, to try to just define some sort of a hypothetical P4, which would be able to process traffic all the way up to the layer 7, so like application layer protocols in a completely compliant way, how we are trying to do it today at layer 2 and layer 3. And of course, we are trying to write a tooling, or at least just play with the idea and try to go try to see how far this idea brings us. The good news is that this is doable. And what's really interesting here is that the good old match action filter logics that we are doing in P4 pretty much is usable at application layer as well. So we have working prototypes for RTP and RTCP, and we also have a working prototype for DNS. We can process these very simple connectionless protocols, and we get nice performance with it. The bad news is that this is not for hardware. For instance, in DNS, in HTTP, you constantly faced with having to process text, textual input. This is not something that you can do in efficiently in hardware or in traditional P4 switches. Of course, you can hack things into P4, but this will never really scale, but not even eBPF. So the other most important data plane programming framework can handle these sorts of workloads. We have a couple of ideas in the paper. So I would like to leave you with these three takeaways. We have to, or at least we believe that it's important to try to extend our understanding of networking and our frameworks towards application layer protocols. We should move the application layer network stack out from the applications, the actual hard-coded application logic, into the data plane, and be able to expose it to a central controller so that we can expose layer 7 network policies to the service mesh controller or the SDN controller. But the way we are actually doing right now, the service mesh is not the best way to do that. How to actually just evolve software-defined networks and P4 into the future, in a bright future where we also just process application layer logics the same as we are doing today with routinely with Ethernet and IP and UDP. We think that full stack SDN and full stack programming frameworks are the future, but how to do that, this is, I believe, is an important future challenge. So that's all.
around these blocks of on chip. That when I say block, is a programmable block which has a dedicated hardware circuit to parse packet at line rate. So this is a very useful resource and can we maximally utilize this resource in an efficient way? That depends on the target architecture. But if I have a capability to take the program, look at the module parser or deparsers, and allocate the code in a way that is amenable to target hardware, that will maximize my resource utilization on the chip. When I say resource utilization, one would be match and action tables, and another would be this dedicated hardware circuit to parse packet at line rate, and that is not available at all over the place. Now, what is the complexity of creating this global parser? Yes, it is a little bit complex. Can we do all the time? Probably no. For most of the realistic scenarios and domain-specific use case, can we do it? I think, yeah, we can do it. And when we cannot do it, we again fall back to simulating parser using some other resources on the chip. So that's the. I hope I answered that. Or if you have any question here.
No, it makes sense. Makes sense. Yes.
Yeah, and the second part about this 5G what you mentioned. So there are projects open source where they do offload some of the tunneling, which is so tunneling is something highly used in telco networks. Is full of the telco protocols are full of tunneling everywhere, and that part is when they program it, this P4 can be used to offload some of the data plane part of data traffic of telco networks to process within a switch, and that gives them very huge flexibility to react at line rate. Another, when you mentioned about the slicing of 5G networks, so the slicing is again a scheduler where they have to allocate channels at very within they have to make a decision for channel location in order of milliseconds, and to react at that level, if there is a programmable device at the edge, not exactly as P4, but I mean, if some way to process packet in some more programmable device at base station, that would definitely help them. So that's what my understanding is. I'm not with little bit of telco experience. This is what where P4 comes into play and allows them to program 5G or 6G future protocols without modifying the hardware with reprogrammable, reconfigurable hardware. Yeah.
Thanks, Hardy. Yes, this is in line with the challenge that, for instance, telco operators are indicating to have with 5G and 6G, which is about how to implement the network slicing and then how to ensure that there is traffic isolation, quality of service, etc. Then following up on that, and it kind of makes sense instead of the next question, and this is perhaps a little bit more for Gabor. And the reason is for you, Gabor, is because you discuss more the SDN aspects, and SDN already experienced a little bit what I have in mind as a question. What I have in mind as a question is P4, it makes a lot of sense in data center environments. Now, my question would be a little bit as it happened with SDN. What are the challenges for P4 when you start considering not only the data center, but also beyond that? I mean, when you start thinking, okay, there are edge computing platforms that are not, in the data center, they are outside, they are networked with the data center, but they are outside. What happens when you have IoT lakes, IoT swarms, when you have deep edge type of scenarios, and all of them are coexisting. So you really have there a lot of packet forwarding within that ecosystem, which is not heterogeneous as potentially or allegedly sometimes a data center is. Do you have any vision about what the challenges are there?
Yeah, so this is a wonderful question, and I think I can only just go back to the first observation that we made in this talk. That the problem is that without actually being able to process packets at the application layer and traffic at the application layer, we just lose the visibility into traffic that would be really necessary to be able to impose the network policies that we want. Just one example that we faced recently, where an edge deployment needed to be connected to the central cloud facility via a service via an SD1. And the problem is that the SD1 itself does not have enough understanding of traffic to be able to process the streams in the way that we wanted. We are handling packets at layer 7 in the edge and in the cloud, but between these two facilities, there is the SD1 link, which does not have visibility into our traffic, so it has to just very, very inefficiently and very tediously reprocess the traffic, apply DPI to understand the traffic that we actually just perfectly know how we want to handle. And the problem here is that, of course, the SD1 does not have understanding of the application layer protocols. So we somehow need to just be able to synthesize all this end-to-end functionality into some application layer processing or network processing architecture. And it's super simple because traditional SD1s, like SD1s, do not have understanding of application layer encodings. So I think that for me that I see that is one of the most important blockers. But of course, this is super challenging because lots of application layer protocols are much more complex than what we can actually process in today's P4 switches. So of course, this is a difficult problem area.
I can say that precisely for the problem that you identified on the visibility of the traffic, once you are in SDN, some of the work that in our case we are conducting on telemetry, it already incorporates deep packet inspection and regular expressions that are coming directly from the network interface cards, precisely incorporating that information to abstract the data and be able to take decisions about exactly what type of flow do you have and what are the characteristics. But you are hitting the nail on the head, actually identifying that problem, which is basically a traffic problem. And that leads perhaps just to one last question, or more a request to have a little bit of comments, and it's towards Marco, which is on the implementation of the load balances, because the load balancers for the traffic, what I'm seeing around is now this trend to just to add new machine learning, deep learning, reinforced learning, all type of fancy approaches in a load balancers just to optimize. And my question, and it is a little bit as the same with Hardik, from the engineering point of view, to which extent there is a trade-off between how complex do you want to make a solution so that it's still worthwhile to have such a complex solution for the problem that you have. Do you have any input in there?
Yes, at least I feel like power of two choices typically works pretty well. So that's simple enough and gives you very good load balancing. So I'm not extremely familiar with real-world products using machine learning for load balancing, but we also looked at this. We basically tried to look into reinforcement learning to understand how to make decisions, because load balancing is extremely hard and it's extremely tough. Sometimes it's really hard to understand where the request should be sent and which servers struggle more or what's happening behind the load balancing. So definitely a rationale to use those type of tools, but it's unclear whether you're going really to beat simpler mechanism like power of two choices, in which you just collect the metrics and then you make simple decisions. So I don't have really an answer to this because we're working on it. also. And so far, I mean, our machine learning is not working well, so we're not beating the simple one. So that's why I would, for now, say that the simple one are better, but that's based on the knowledge that we have right now.
Well, I'll try to be positive. As far as there are challenges, there is a space for us to grow. So it's good that not everything is easy, in a way.
Absolutely.
Yeah. I was going to say, I think we still have NEC, which is one of the co-organizers. I'm not sure if Roberto from NEC has any open questioning here, or perhaps it's time to say yes. Please go ahead.
Maybe a final one, probably elaborating on the discussion you had before with Gabor and also with some indication from the presentation of Matti that when he was saying that the firewall they are implementing for the MARSAL project is actually based only on some of the characteristics of the traffic, like the size of the packets, right? So I don't know if you see that P4 can have a place to improve the cybersecurity in general of the network, or the limitations on the traffic observability are very limiting there. So I don't know if you have an opinion. Maybe Gabor is the one that has presented something more similar to this, even if it wasn't about cybersecurity. But if the rest of the speakers, if you have an opinion, it would be great to know about it.
No, I think that's also fully agree. Yeah. So like this is also a super important aspect.
From my side, I think my understanding is that it works as a good solution, provided that it works in conjunction, of course, with the telemetry system, because then you do have the ability to include rules in the target that might actually help in topics related to cybersecurity. Cybersecurity is, however, a very broad term, so it would really matter. It would be relevant here to figure out exactly what do we mean. I mean, do we mean to identify malicious requests, flows that should not be there but are there, and that may be related to, for instance, something like a crosstalk or traffic isolation. So there are so many. There is such a broad range cybersecurity that it would first need to be determined what is the use case. But in any case, the answer I would say is yes.
Okay, thank you very much for the answer. Yeah, I agree. Cybersecurity is a complex topic that is composed by completely different things. Yeah. But let's hope with the usage of P4 we can improve current solutions.
Yes, let's do that, and that might give us a chance to have a follow-up event on precisely P4 in conjunction with cybersecurity. What I would like to do is to thank all the speakers, Filippo, Hardik, Marco, Matti, and Gabor, for their time, the co-organizers of the webinar, and of course, all the live audience that has been watching this stream live, and everybody else who is going to be watching this video afterwards. Very much appreciated. Have a nice day.
Thank you. Bye.
Thank you very much.
Yes. Bye-bye.